Hi students, good evening. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall discuss circle theorems. Theorems on circles. Circle theorems. Or you can say theorems on circles. Please, it is important to view the videos on circles first, the introduction to circles, and the meaning of the terms used in circles. It is recommended that you view that video prior to viewing this video. In this video, we shall review those basic terms. We are going to review them, and we shall list some theorems on circles. It is a lot of them. We are not going to list all of them tonight because we would like to solve some questions as well. It is important to learn it, to learn it this way, as piecemeal approach, to learn it in chunks. We are going to learn some theorems tonight, and we are going to solve questions, past questions actually. The questions we are going to solve are questions from a CSEC, that's the Caribbean examination, and then the WASSCE, which is the West Africa Senior School Certificate Examination, and also JAMB. Okay, we're going to solve some questions from those exams. So we will do some theorems tonight, then solve questions that are where we will apply those theorems. So this is going to be part one. This will be part one. So it's a lot of theorems, but we are going to do it in piecemeal approach. We are going to do it piece by piece. We will do some tonight, solve questions tonight, and then we will continue with other parts of the video. So let us quickly review. Let's review some terminologies in circle. Okay, so we say that, and what I'm explaining now, if you go to this website, www.samdomforpeace.com, www.samdom, Samuel Dominic, the short form is Samdom for peace. Of course I'm for peace, of course. You know I'm for peace. I'm not for war. I'm for peace. So www.samdomforpeace, that's my nickname, samdomforpeace.com. You will see, you click on circle theorems, and you will see the transcript of this video. Okay, and the questions already, I have my laptop here, so I'm going to pull it directly from the side. The questions. So the questions and the solutions, they are already right now on the website. They are already, as I'm explaining this. Okay, so they are already on the website. So it will save us time because we have a lot to cover. We have a lot to cover. Circle theorems are a lot. Okay. So let's review some terms in circle. We say that a circle is a locus of points equidistant from a fixed point known as the center. Please don't laugh at my circle, okay? Please do not laugh at my circles now, don't. Okay. If you want to laugh, you can laugh, it doesn't matter. Okay, so a circle is a locus of point equidistant from a fixed point. What do we mean? If we have a fixed point here, we have a fixed point, And we have several points that are equidistant. Equidistant means equal distance. Equal distance. Equi is equal. Equal means equal. Equilateral. Equal sides. Lateral means sides. Equiangular. Equal angles. Okay? Equity, equality, equanimity, equation, equality. Okay, so if we have a fixed point, that is the center, and we have points equidistant from this fixed point, we have points that are equidistant, equal distant from this fixed point. Okay? If we have points equal distance from this fixed point, the locus of those points form a circle. That is what a circle means. Locus of points equidistant from a fixed point. And that fixed point is known as the center. The center. Okay? In WASSCE, in JAMB, they normally use O to denote the center. They normally use O to denote the center. But please, 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 I repeat, please, 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 if you are not told that O is the center of the circle, do not assume, no, don't assume that, hey, this looks at the center as the center. Or even if they don't put O, if they don't put O, but you look at it, it might look like the center. No. In circle theorems, we don't assume. We don't do that. We are going to discuss the theorems and we are going to use those. Don't make up your own unless you can prove it. You're welcome to make up your own if you can prove it. Okay, but do not assume. No, we don't assume. Okay, so that is what we mean by the center. I mean by the circle. Equal distance from a fixed point. That fixed point is known as the center. Okay, and then the distance from the center to the whole distance round the circle. The total distance round the circle is the circumference. So we've mentioned center. We've mentioned circumference. Please. This is Nigerian way, center, okay? Americans will write it this way. It doesn't matter. Okay? But this is, you know, this we do it in Nigeria, so I'll be using this. But Americans watching me, don't be scared. Don't be, not scared. Of course, Americans are not scared anyway. We are not scared. Do not say, hey, he got it wrong. This is a British way. Okay. Yeah. But a lot of these the questions here, they use center like this. Okay. So we've talked about circumference is the total distance round the circle, is the circumference. Now, the distance from the center of the circle to any point on the circumference. So this is the circumference, the total distance round. Now, distance from the center of the circle to any point of the circumference. Any point of the circumference is the radius. The radius. Okay. Singular is radius, plural is radii. Radii. So we've talked about radius. So as you can see here, right, what we just did, because we are going to apply this. If you have lines like this, okay, if you can see here, if you join this now to form a triangle, because this is the radius here, this is the radius here, that tells you automatically that this is an isosceles triangle. This length is equal to this length. Okay, isosceles triangle, two sides are congruent. Okay, so that implies that this angle here is equal to this angle. We call it the base angles of isosceles triangle. Base angles of isosceles triangle. And it can also be this way. It can also be like this. If you have it like this, provided its distance from the center to any point of the circumference is the radius. So if you have it this way, and if we join these to form a triangle, this is an isosceles triangle. And this, because these two sides are congruent, these two angles are also congruent. We call it the base angles of isosceles triangle. Okay? Then the 2 times the radius gives you the diameter. The diameter is the longest chord. The diameter is the line going, the line that touches any 2 points on the circumference of the circle but passes through the center. Okay, so that is, like line segment. The line segment that passes through the center of the circle and it touches any 2 points on the circumference. Okay, just like your definition of chord. However, with the diameter, it is the longest chord because it passes through the center of the circle. So, and it is 2 times the radius. Okay, 2 times the radius. Now, we now come to a chord. So, if let's say you have the circle, then you have a chord. Let's say you get an orange. I know an orange is spherical, but assume it's circular, okay? And you cut it, like you cut the top part, or cut the top part. So you have a chord. This is a chord. A chord divides the circle into what we call 2 segments. 2 segments. So let's say we have this as A, B, C, D. So this chord divides this circle into 2 segments. So we have A, B, C, and then A, D, C. Now this is what we call the major segment. Major segment, of course, because it's bigger. And this is the minor segment. Minor segment. And it mustn't be just like this. It mustn't be just like this. It could also be like this. It could also be this way. It could also be like this. And when you have it like this way, if you have it this way, then this here is the major segment, and this is the minor segment. Okay? So we talked about chord, talked about segment. Yeah, because we're going to do some applications of these angles in the same segment. Okay? It has to be in the same segment. So I just want to show you, when I'm talking of segment, what it will be. Alright. Sector, do I need sector here? Area of sector, major sector, minor sector. Well, let me talk about it although probably we will not use it tonight. But when we have something like this, let's say we have the circle, and then we have a cut. Okay, let's say we have a cut from this is the circle center O, and we have cut here, 2 cuts. So if we split this here, this will look like this. This is going to look this way. This is going to look this way. Now, later we'll discuss this when we deal with area of sectors and length of arcs. Okay, we will talk about it again when we deal with arcs and sectors, length of arcs and areas of sectors. So if you look at this now, this right here, this right here, right here. I'm going to use a yellow chalk. This right here is an arc, So this is the minor arc, this is the minor arc. And this here is the major arc, The major arc. Now, but this area right there, this area right here, this here, because that's just like in segment we said area, because it's the whole thing area. Arc is just part of the circumference, arc. Now this area right here is the minor sector, and this is the major sector, Okay, so we talked about arc, we talked about sector. Alright, but we are going to still deal with this when we do the videos on calculating the length of arcs, sectorial angles, area of sectors. Okay, we shall talk more on this. Now the next thing we shall discuss is the semicircle. Half a circle. Semicircle. Semi. Will you say semi or semi? Semicircle. So if we have a circle, and this is the center of the circle, and we just cut it in half. Okay? I know some people will say this looks elliptical, what I just drew now. Some people will say, hey, Mr. C, it looks elliptical. So if we have this now, half of the circle is what we know as the semicircle. So these are 2 semicircles. This is a semicircle, this is a semicircle. So number 9, it says semicircle. Okay, so we talked about sector already and segment. Okay, now we're going to discuss what we call the tangent to a circle. So when we have a circle like we have now, okay, if we have a line, just a straight line that touches the circumference at only one point, has to touch the circumference at only one point. Let me draw this again. A straight line, we have a circle, I will have a straight line that touches the circle at only one point, a straight line. Okay? That is a tangent to the circle. Okay? So if we call this maybe AB, AB is a tangent. We can also have it this way. Just if it touches the circle at only one point, only one point, CD, line segment CD is also a tangent, tangent to circle. A straight line that touches the circle at only one point. Okay, straight line that touches the circumference of the circle. A straight line that touches the circumference of the circle at only one point is known as the tangent to the circle. Yeah, and the point that it touches it is the point of contact. Here, this is the point of contact. Point of contact. Or you can also say point of tangency. Point of tangency. Point of tangency. Tangency. Okay. So line segment AB is a tangent to the circle. Line segment CD is also a tangent to the circle. Yeah. And the point of contact, the point that it touches the circumference of the circle, is known as the point of contact or point of tangency. Okay? So number 10, we've talked about tangent. Tangent to circle, to a circle. Okay? The next thing we'll talk about is a cyclic quad. A cyclic quadrilateral. Cyclic quad. So when you have a circle and you have if you have a quadrilateral, a quadrilateral inside a circle whose vertices, a quadrilateral is any four-sided polygon is a quadrilateral, like your rhombus, your rectangle, square, kite, parallelogram. Okay, so a quadrilateral is a four-sided polygon. Okay, and then a cyclic quad. A cyclic quad is a quadrilateral inside a circle whose vertices touch the circumference of the circle. That is a cyclic quad. Cyclic quadrilateral. Cyclic quadrilateral. So you have a quadrilateral inside a circle and the vertices, the four vertices, touch the circumference of the circle. It's a cyclic quad. Let's draw more. You can have it this way also. Provided that the four vertices touch the circumference of the circle. You can have it this way. I actually wanted to draw a palm. Okay? That's the cyclic quadrilateral. All right. For what we shall discuss tonight, what we shall discuss tonight. And of course, you know some triangle theorems. Please, it's my assumption that you you know some triangle theorems as well. Okay, because you might use them we will use them. All right, let's there are still more, but if more comes up, okay, from the questions, if more comes up, we're going to talk about it. Now let's make angle at a point. Okay, angle at a point, of course, you know, is a 360 degrees. Angle, the interior angles of a cyclic quad, you know, the sum of the interior angles is 360. Angle at a point is also 360. So, actually, I might write number 12 is the main thing we talk about, circle. Well, we should be number 1. We should be number 1. But that's okay. So, we have at least have an idea of this. This is just a review of what we discussed earlier. Okay, most of the things we discussed this earlier. All right, we shall now state some circle theorems and do some explanations before we now solve questions. So let us state some circle theorems. Some theorems on circles. Okay, theorem number 1. Theorem 1. Angle in a please, like I said, what I'm explaining is on the website. Okay, you can write, but I will be showing you that rather than writing the whole thing again, because I have already written it on my website. I have already written it on the website. So to save time in this video, we have a lot of things to cover. You can write, but I encourage you to go to this website and click on circle theorems and read it. Okay, as you're viewing the video, you can read it. Theorem 1, the angle in a semicircle is a right angle. Angle in a semicircle is a right angle. Okay, angle in a semicircle is 90 degrees, which is a right angle. So this is what we mean here. Could be like this. Semicircle, remember, is the center. Okay, so it could be like this, folks. Just look up. It could be like this. Here, and look. Angle in a semicircle. What do we mean by angle in a semicircle? It has to be a semicircle, which means it passes through the center. It passes through the center of the circle. Then it is not this angle, no. It is this angle here. It's 90 degrees. Angle in a semicircle. It's 90 degrees. Another example, can have this. This is the center. Let me write center O, okay? Center O. And it could be like this. Could be like this. It has to be a triangle, but it has to pass, it has to be a semicircle. So this is 90 degrees. That is what it's saying. That is 90 degrees. It could be like this also, because it could be several ways, okay? Center O. Center O. And look at what I'm doing now. When you have it this way, you have it this way. This is 90 degrees. That is what it's saying. Angle in a semicircle. Do you get the concept now? Like, do you get the concept? Okay, let's draw more. Center O, you can have it this way, passing like this. Then it could be like this. It could be like this. Here, here. This one is the right angle. Angle in a semicircle is a right angle. Angle in a semicircle is a right angle. So do you see what I mean? Because, you know, anytime, let me give you this advice. Anytime you see the circle and there's a center and there's a diameter, okay, watch for this theorem. If you see a circle, there's a center, there's a diameter. Of course, diameter means it must pass through the center. Okay? If you see a circle, there's center, there's diameter. They might be asking you this theorem. They might. They must not draw the triangle for you. That is the problem. Okay? They must not draw the triangle for you. Sometimes you would have to complete it on your own, provided you're doing it correctly. Provided that you are doing it correctly. Sometimes you would have to complete the triangle on your own. Okay? But just know the things that are right angle. Angle in a semicircle is a right angle. Or angle in a semicircle is 90 degrees. Okay? Now, let's do theorem 2. Theorem 2. Angles in the same segment of a circle are congruent. Angles in the same segment of a circle are equal. Okay? Angles in the same segment of a circle are equal. Same segment, folks. Same segment. Same segment. Same segment. Okay, let us see what this means. If we have a circle, okay, and you know, I'm going to show you several ways, but let me start with the clearest way. So if we have a chord here, so this is the major segment and this is the minor segment. That was what we said. This is the major segment and this is the minor segment. Okay? Now, this is what this is saying. If I have the same segment, okay? Let me start with this. I can have it this way, look. It must not be from the center, it must not be by the center. Okay, but we are going to look at several, okay? So look at what I'm doing now. I can do this, bring it here. It starts from the one end point of the chord to the other end point. Okay? And I have another one like this. Like this. What this theorem is saying is that this angle is equal to this angle. So if I have theta, if I have this as theta, this is also theta. That is what this is saying. Angles in the same segment. That is what it is saying. And I can also come and have it this way. Provided it starts from the one end point to the other end point and it touches it. This is also theta. Theta. because they are in the same major segment. Now let me say this. They must not, they must not draw the chord for you. No. No. They must not draw the chord for you. And they will not. Sometimes they will not. Okay? So, as you see, I have now erased the chord. This is now major segment. The chord must not be drawn. So, this is just showing you clearly, just to explain the example. We are going to look at more. So, let me go ahead and put the chord. Okay. Now here, if we also, this is minor segment. If we have, it comes from one end to another end. See that? It comes from this end to this end. If this is beta, this is also beta. Angles in the same segment, because these angles are in the same minor segment. They are in the same minor segment. Hey, these must come from one endpoint of the chord to the other endpoint of the chord. Look, if you have something like this, let's say you have a chord. Okay, so you have this here, like this, and then you have this here, and it's like this. I beg you. You see this? No, no, no. No! Because it doesn't touch the other end of this chord. It didn't touch it. It did not touch the other end of this chord. So, no, this will not apply. It will not. Okay? Angles in the same segment. What if I have something like this now? Because it must not always be like this, okay? You can have it like this. Here to here, here to here, here to here. You see this? See this? If I call this psi, 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 psi. You see, it's angles in the same segment. Angles in the same segment. And I'm using Greek words if you didn't understand what I'm saying. Okay, I'm gonna use English for now, okay? I'm gonna use the English alphabets, okay? Going forward, I will use the English alphabets, okay? So, you want me to write it X, X, X? Okay, I can. I can write it X, X, X. So, if you're not familiar with the Greek alphabets, maybe you have not learned trigonometry. Go to trigonometry.appspot.com on my website, www.trigonometry.appspot.com. And you go to my main websites, you can also go to this website and click on Samuel Chukwuemeka Tutorials. Okay, when you go to this website, click on Samuel Chukwuemeka Tutorials or Chukwuemeka Samuel Tutorials. Then click on mathematics, click on trigonometry, and you'll see it. You just learn the Greek alphabets. You're going to use them in trig, okay? So, but here, let me use X and Y and the rest of them, English alphabets. Unless they ask a different thing. Anything they ask in the past question, I will use it that way. Okay, so do you see what I'm talking about? Okay, angles in the same segment of a circle. Now, they must not put that chord. So let's see if we, I know we're gonna do more problems, but let's do another one. We can have something like this. Just like this. Okay, I didn't put the chord now. I didn't put any chord now. But hey, it is still angled in the same segment. If you join this chord, you see that it is angled in the same segment. Okay? It just tells you that this, if we call this Y, then this is also Y. Angles in the same segment. Does that make sense? Okay, can you guys do this here? Can you do this here? So here we can see the angles that are equal. Now, can you guys do this? Let's say we have this. Circle center O, and we have this. Okay, look at this now. If I ask you to find C, D, find C and D. Here, find angles C and D. Like, of course, we just did this. Okay, we're going to use theorem 1 and theorem 2. So as you can see here, this is a semicircle. This is a semicircle. So C is 90 degrees, and your reason is, I normally put 3 dots. Reason, now, with circle theorems, you must, I repeat again, you must state your reasons. So you don't assume anything. You've got to state your reasons, except for JAMB questions, which you're timed, okay? You have to solve it. Gotta solve it fast. Solving it timely and accurately. Not just accurately, but timely. Then you don't need to write all those. But if you're on multiple choice, WASSCE questions, WASSCE. But if you're doing the essay, theory, the theory part of mathematics, WASSCE, or you're doing the CSEC, the Caribbean examination, you've got to state your reason. You've got to. Okay? So C is equal to 90 degrees. Reason, angle in a semicircle. Angle in a semicircle. Angle in a semicircle. Okay? Then D is equal to C. D is equal to C. Okay? Reason, angles in the same segment. Angles in the same segment. Angles in the same segment. So this implies that D, or you can also say actually that D is also equal to 90 degrees, D is equal to 90 degrees because it's still angles in this angle in a semicircle. You can also have it that way. So you see, some questions you can do with several, you can use several, at least more than one theorem, and you still get the same answer. Some of the questions. Alright, theorem 2. angles in the same segment of a circle are equal. Right? Let's do theorem 3. We will do some, okay, we're going to do some theorems at least before we start solving problems. Theorem 3. Okay, I want you to listen to this one. The angle which an arc of a circle, the angle which an arc of a circle subtends at the center is twice the angle which the same arc subtends at the circumference, at any point in the circumference, at any point on the circumference. I come again. The angle which an arc of a circle subtends at the center is twice the angle which the same arc of the circle subtends at any point on the circumference. This theorem is a little bit tricky, but I'm going to explain it to you. Just look up. So let's have a circle. Here we're going to deal with center. Now the first theorem, angle in a semicircle, it deals with center because that is half of a circle. Second theorem, angles in the same segment, it may or may not deal with center. We saw that. It may or may not deal with center. Now this third one deals with center and circumference. Okay? So we have a center. Let me start with the clearest example, then we look at some other confusing ones. Not, well, I wouldn't call it confusing, but not so clear. Okay? Now, if we have this here, this is what this theorem is saying. If we have this like this, so look at this here. Do you see this here and this? Do you see how they are? Like this. So you have this arc here. You have an arc here. You have an arc. This minor arc subtends, S-U-B-T-E-N-D-S, subtends this angle at the center. Let me call it C. And this same arc subtends this angle at the circumference. I call it D. This theorem is saying that C is equal to 2 times D. That is what the theorem is saying. C is equal to 2 times D. 2D. That's what it's saying. Okay. Let's see about the major arc. Okay, or let's look at it another way. Let's look at it this way. Okay? What if the major arc subtends the angle at the center? Okay, so here we can have a reflex angle here. Now, do you see how this is going like this? Okay. So this same thing, if we have it at any point on the circumference, the same arc here, you see this now. I'm using yellow chalk, but you know what? Let me use double because I don't know how yellow chalk appears. So let me use this. Do you see how this like this? Do you notice this? This, and then this, and then this, and this. See that? Has to work that way. Because sometimes if I give you this and ask you to find this, so let me call this E and F. E and F. Sometimes they will give you E and ask you to find D. That's the thing. Sometimes they'll give you E and ask you to find D. So this is saying that E is equal to 2 times F. Okay? 2 times D is 2D, 2 times F is 2F. That is what this is saying. That is what this theorem is saying. Because you look at this now, this major arc subtends E at the center. And that E is twice F, subtended by the same major arc at the circumference. Angle at center is twice angle at circumference. Angle at center is twice angle at circumference. Okay, let's look at more examples. Now this is center O. Let me say O is the center of the circle. O is the center of the circle. This is the center. You can have this way. Like this. Please, look at the confusion that some students do. They might think that these are angles in the same segment. No! If it was angles in the same segment, it will look like this. If it was angles in the same segment, it will look like this. It will look like this. You see the difference? Do you see the difference between this and this? This is theorem 3. And this is theorem 2. Theorem 2. Angles, this is theorem 3 and this is theorem 2. These angles in the same segment. Do you see the difference here? This is from the center. This is not even from the center. Okay, and if it's from the center, you see, it's not like this. I know some people will say, but it has the chord. If you draw a chord, some people will say, okay, if you draw a chord, what about that? However, this didn't touch that. It has to touch. Do you see that this touched this circumference? See, this touched it. If I have the chord here, and this is the major segment, okay? And if I have the chord here, and this is the major segment, you look at this here, it touched the circumference, the two of them touched it. But here, only one touched it. The other one is at the center. It didn't touch it. So please, this is a common mistake. That people will say, okay, this and this are congruent. No. This and this are equal. Yes, this one and this one. If this is A, this is A. Okay, but if we have this, and they will not put, sometimes they will not even put this code. Okay, so let me erase it. You have this. If I call this a E, F, G, H, I, let me use M and N. So what this is saying is that N is 2N. That is what it's saying, that M is 2N. Do you see that? This is a common mistake, please. But here, A is equal to A. Angles in the same segment. Okay? Let's look at some more. On theorem 3, you can have it like this. This is center O. Center O. You can have it like this here. If I call this K and then P, P, you can have it like this. So here, this means that P is equal to 2K, 2K. P is equal to 2K. Okay? You can also have it this way. Let's see. Center O. Did I draw this one now? Let me see. That's the way I want to draw it. That's the way I want to draw it. Please, the main thing I'm looking at here also is, look at this here. Do you see how this one went like this? Like this? You see, it has to follow that same procedure. See that? You see how this one went like this? See that? Has to follow that same procedure. Okay? There's another one I want to draw. Probably we'll see it, you know, as we solve questions, we'll see it more. There's some I'm figuring in my head. But let's move on, okay? Let's move on. At least you have the idea now. Angle at center is twice angle at circumference. Okay? And it deals with center. Alright? Okay, theorem 4. Theorem 4. Theorem 4. Let's go to cyclic quad now. The opposite angles of a cyclic quadrilateral are supplementary. The opposite angles of a cyclic quadrilateral are supplementary. The opposite angles of a cyclic quadrilateral are supplementary. So, two angles are supplementary if their sum equals 180 degrees. And two angles are complementary if their sum equals 90 degrees. Okay. So here, this theorem deals with a cyclic quad. Okay, we've talked about cyclic quad. So, any 4 points any four, the four vertices is the quadrilateral and the four vertices must touch the circle. Okay? So what this theorem is saying, if we have A, B, C, D, what this theorem is saying is that A plus B is equal to 180 degrees. Sorry, I am so sorry, A plus D. A plus D. Opposite angles of a cyclic quad, yeah. Opposite angles of a cyclic quad are supplementary. Okay, A plus D is 180 degrees, and then B plus C is 180 degrees. Opposite angles of a cyclic quadrilateral. Okay, let's look at some more. I'm trying to get this here and then this here. E, F, G, H. So what this is saying is that E plus G is 180 degrees, and then F plus H is 180 degrees. Opposite angles of a cyclic quadrilateral, okay, are supplementary. And don't worry, we'll have it now here. We'll do more. Okay? So this one is pretty straightforward, right? Yeah. Now let's look at theorem 5. We'll do a few more, then we can solve some questions before we call it a night. Okay? Theorem 5. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay, so we are still dealing with cyclic quadrilaterals. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angles, to the interior opposite angle. So let us look at some examples here. We have a circle and we have a quadrilateral inside it. So this means a cyclic quadrilateral. A quadrilateral inside a circle whose vertices touch the circumference of the circle. So let's have it this way, folks. If we have this, we have this, we have this, we have this, like this. Okay? So let's say we have this A, C, D, E. Let me use a yellow chalk here. F. Here. G. Here. P. Here. K. So look at this here, okay? Theorem 4, we did opposite opposite angles of a cyclic quad, okay, opposite interior angles of a cyclic quadrilateral, the sum. With theorem 4, the sum of the interior opposite angles of a cyclic quad are supplementary. But theorem 5 is that the exterior angle of a cyclic quadrilateral is the interior opposite angle. Okay, so this is what this theorem is saying, that K is equal to E. Because see here, you look at an interior angle and this is the exterior angle. And the interior opposite angle is E right away. Do you see E? Is E. Okay? The interior opposite angle. Then you look at here, you look at a P, interior opposite angle is what? D. The interior opposite angle. Just, you look at the interior angle that is on the same straight line with, and just opposite it is the interior opposite angle. Here, you look at K, the same straight, the interior angle that is on the same straight line is A. Opposite it is E. For F, the interior angle that it is on the same straight line is D. Opposite is C. So F is equal to C. And for G, the interior angle that it is on the same straight line with is E. Opposite it is E. And G is equal to A. So this is your theorem 5. Okay? The exterior angle of a cyclic quadrilateral is the interior opposite angle. So you just check what is the interior angle that it is on the same straight line with. Opposite it is the exterior angle. Is the opposite it is the opposite interior angle. Okay? You have the exterior angle. Check the interior angle that is on the same straight line with. Opposite that interior angle is that exterior angle. Okay? So P is equal to D, K is equal to E, G is equal to A, and F is equal to C. Theorem 5. Okay, let's do theorem 6. Theorem 6. I think we have about so theorem 1, angle in a semicircle is 90 degrees. Theorem 2, angles in the same segment are equal. Theorem 3, angle at center, the angle which the arc of a circle subtends at the center of the circle is twice the angle which the same arc of the circle subtends at any point on the circumference. Theorem 4, the opposite interior angles of a cyclic quadrilateral are supplementary. Okay? Theorem 5, which we just did. Okay, the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Theorem 6, we're going to deal with now tangent to circle. We'll do some theorems on tangents and then we can solve problems. Theorem 6, the radius of a circle is perpendicular to the tangent of the circle at the point of contact. At the point of contact. Okay, I'm gonna, let's look at this. The radius is perpendicular to tangent at the point of contact. The radius of a circle is perpendicular to the tangent of the circle at the point of contact. Remember, we say it is called point of contact or point of tangency. So let's say here, now this theorem deals with center, radius, okay, because radius is from the center. So let's say we have the center of the circle, O, and we have a tangent to circle. So what this theorem is saying is that when you have the radius, okay, which is a line drawn from the center of the circle, but if you draw it so that it touches the tangent at the point of contact, that this is 90 degrees. That is what this is saying. Radius is perpendicular to the tangent at point of contact. If we have it this way, okay, and it must not be only one tangent. It must not, okay? It must not be only one tangent. Let's have it this way, for instance. One, and another one. Let's have two tangents here. We can actually have it like this. Don't laugh at my straight line. Okay? So what this is saying is that when you have the center of the circle, O, what this is saying is that this, from here to here, which is the radius, to the point of contact, and from here to here. So this is saying that this radius is perpendicular to the tangent. This radius is perpendicular to the tangent. That is what it's saying. And you can even have another one. You can have another one. You can have another one like this. Oops. Look at my straight line, tangency. Okay, what this is saying is that this is the radius is perpendicular to this at point of contact. That is what this is saying. Radius is perpendicular to the tangent to the circle at the point of contact or at the point of tangency. Okay? All right. We do one more theorem and we can, there are so many theorems, okay? But let's stop at 7 for tonight. Let's stop at 7 theorems so we can solve questions at least. Because, I don't want to compact all these theorems and then, okay, Mrs. C, I gotta solve problems. You've been going off, you've been teaching us all these theorems. Let's start. Let's do something with it. Okay. Okay. So, yeah, we will not finish the whole of them tonight because I don't want to pack a lot of things in your head. I want to take it as piecemeal approach, in chunks, okay? Theorem 7, two tangents to circle. Two tangents now. Theorem 7 deals with two tangents to a circle. Okay? Two tangents to a circle drawn from the same external point are congruent in length. Two tangents to a circle drawn from the same external point are equal in length. Two tangents to a circle drawn from the same external point are equal in length. Okay? So you have it this way. Let's look at this here. So let's say we have this deals with two tangents, okay? So let's say we have an external point, but let's draw a tangent first. Because tangent touches the circle at only one point. Touches the circumference of the circle at only one point. The point of tangency. So let's say you have that. And you have another one, another tangent. There you go. So as you can see, this is drawn from the same external point. You have two tangents to the circle that are drawn from the same external point. So you have this here, this tangent and this tangent. What this theorem is saying is that these are congruent. They are congruent. That's what it's saying. Okay? And later we can go to what, you know, if you have with that. Just for you to know, they're congruent in length. Now you might have something like this as we move on. Maybe you have this at the center. But I just want you to know that they are congruent in length. That's the main thing that I want you to know for tonight. Okay? We have another theorem that deals with this, but I don't want to go into that. Whether it bisects the angle formed. I don't want to go into that, okay? Just know that they are congruent in length. You might have this as the center of the circle. Or even if it's not the center, just know that the two tangents, provided they are drawn from the same external point, that they are congruent in length. Just know that. Okay? Two tangents to a circle drawn from the same external point are congruent in length. So what I mean is that from here to here, and like let's say we have AB, and here we have CB. So what this is saying is that line segment AB is equal to line segment CB. That is what I mean. Two tangents to a circle drawn from the same external point are congruent in length. Does that make sense? Okay, now we have more work to just do depending on the questions we are asked. So but just for now, for tonight, know these 7 theorems for tonight. And we still have a lot more to cover. But let us now start doing some work. Okay, let's start doing some work. Let's do some work. Let's do some examples on what we have learned so far. So I have the questions here, and I'm gonna pull it from my laptop. Okay, like I said, it's on the website. So. Okay, number 1 question I have here is from CSEC. So it says here, this is the number 1 question. So I have this circle here. Well, let me draw this circle first. So we have a circle. Okay. And we have here we have this. Okay. ADCE. And we have another one like this, B. have this. Okay. This is a CSEC. It's a past question from CSEC. And then have the line segment from A to C. Okay. And you have 28 degrees here. 28 degrees here. And you have 46. You also have from B to D. Okay. And you have 46 degrees here. So, and it has the center around here, center of the circle. Okay, it says here, the diagram below shows a circle where AC is the diameter. AC is the diameter, so this is the center of the circle. B and D are two other points on the circle. B and D, two other points on the circle. Okay. And DCE is a straight line. Okay. Angle CAB is 28 degrees. So angle CAB is 28 degrees, as you can see, CAB. And then angle DBC is 46 degrees. Angle DBC is 46 degrees. This means angle at the center. That is what it means, angle at the center. So it says calculate the value of the following angles. Calculate the value of the following angles. And show detailed working where necessary, and give a reason to support your answers. Okay. They say you should calculate angle DBA. Angle DBA. Please, I have solved this, and I think I really, I think if you can observe for yourself and let me know. But I think I really broke it down, honestly. Like, I'm doing this video for, for visual learners, those who would like to at least see what I'm doing. So I'm not going to write the reason, I will say it out. I will say the reason, but if you go to the website, the way I solved it, I stated the reasons. Okay, but because of time, because this video is getting long, because of time, I will just state the reason. Okay, and you just go on my website and you click on the answer and you see the reasons. Now let me say this. After doing a few questions, I would like you to, when you're watching the video, when you watch my videos, pause it. Okay, for this one you can look at it, but normally you pause it and try it on your own. Okay, don't look at the answer all the time. Yeah, try it on your own first. Then you compare your answers to mine. Okay, so that's the thing. So I stated it well, honestly. Okay, DBA, I'm gonna use yellow chalk. DBA is this angle here. They want us to get this angle right here. DBA, as you can see, DBA. So this angle here. Okay, now you look at this here. You can see right here that you have DAC. DAC is 46 degrees, because you see these angles in the same segment. Angles in the same segment from D to C. As you can see here, DAC here already is 46 degrees. I don't know whether they asked it, DAC. Oh, that's the second question. That's the second question they asked. Okay. As you can see, DAC is 46 degrees. Reason, angle in the same segment. That's the second question. II, angle DAC. Yeah. It's 46 degrees, angles in the same segment. As you can see. Now, DBA. Now, look at this here. This is angle in a semicircle. You look at this here. This is a semicircle. Because this, the diameter. So, angle in a semicircle, this whole thing is a semicircle. So, let me just call this X. I can call it X. Let DBA be X. Let DBA be X. So, X plus 46 is 90 degrees. Reason, angle in a semicircle. That's the reason. Okay? So, X is 90 minus 46. So, this is 4. This is 44. 44 degrees. So, angle DBA is 44 degrees. Next one, angle DAC is 46 degrees. Reason, angles in the same segment of a circle. Okay? And then the last one, III, is angle BCE. Angle BCE. Angle BCE. BCE. So they're looking at this angle here. BCE. So as you can see, ABCD is a cyclic quad. It's a cyclic quadrilateral. ABCD is a cyclic quadrilateral. And then this is exterior angle. Exterior angle of a cyclic quadrilateral. So this angle here, this angle right here, is the angle on the same straight line with it. Opposite it. Okay. I'm trying to wake up my laptop so I don't have to keep logging in. So this angle here is the angle in the same straight line. Opposite it. So this is the exterior, this is the opposite interior angle to this exterior angle. Okay, so this exterior angle, angle BCE, is equal to 46 plus 28. 46 plus 28. Reason, exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay, so this gives us 74 degrees. And that's it. That's it. Okay? That's it. I should get it right, I think so. Okay, let's do question 2, folks. We have several questions to solve tonight. Then we can call it a day. Do you get it? Does it make sense? Okay. Question 2. Question 2. Question 2 is JAMB question. So we have a circle. We have a circle. We have it like this here. We have X. We have and this is 130 degrees. Okay, so it says if O is the center of the circle in the figure above, find the value of X. And it gave the multiple choices. I mean, this is JAMB question. So it gives the multiple choice. So here, O is the center of the circle. So we should be looking at angle at center and angle at circumference. If we come here and you see this is like this, because this is like this, so this should be like this. Okay. So this here, if I call this Y, if I call it Y, okay, if I call it Y, like I said, I stated these reasons on my website. So I'll be stating the reasons verbally. Okay. So let me call this y. Y is equal to 2 times 30. 2 times 30. Reason, angle at center is twice angle at circumference. Okay. So y is equal to 260 degrees. Y is 260 degrees. Okay. Then x plus y is 360 degrees. X plus y is 360 degrees. Reason, angle at a point. Angle around a point. Okay, angle around a point. O is the center of the circle, point O. So x will be 360 minus y, which is y is 260. So 360 minus 260 is 100 degrees. That's it. That's it, folks. Okay, x is 100 degrees. All right. Okay. Next one. Let's do 2 more. Let's do at least 2 more, and then we can call it a night. Okay. Let's do 2 more, and we can call it a night. Question 3 is a WASSCE. Question 3 is a WASSCE. WASSCE multiple choice. Now I have both WASSCE multiple choice and WASSCE theory. Okay. I'm doing it like it is on my website. Okay. Question 3 is WASSCE. We have this diagram here. I hope you guys understand the reasons. Okay, the reasons I gave. So you have this is actually a cyclic chord. You have something like this. Have something like this. Okay. So you have U, V, W, U, V, W, Y. U, V, W, Y. You have X. Have something like this here. You have X here. And you have 8X. And you have O. Normally they use O to denote the sender. For JAMB and WASSCE, they normally use O. But let me repeat, please. They have to tell you that O is the center of the circle. Otherwise, do not assume. I repeat, they have to tell you that O is the center of the circle. Otherwise, do not assume. So it says here, the diagram is a circle with center O. U, V, W, and Y are points on the circle. Find angle UVW. Find angle UVW. Okay, find angle UVW. So it says here UVW. So they want us to find this angle here, this angle right here. Okay. So look at this here, folks. So this is 8x. See, now this is angle at center and this is angle at circumference. You see how it was? Now, but this here, O, this is center O. This x, this here should be 2x. This should be 2x. 2 times x. 2x. Reason, angle at center is twice angle at circumference. That's the reason. And then you can now do 8x plus 2x is 10x. Okay? Now this 10x should be equal to 360. This 10x should be equal to 360. 8x plus 2x is 360. 8x plus 2x should be equal to 360. Reason, angle around a point. So 10x is 360, so x is 360 divided by 10. That is 36 degrees. That is x. Okay, now 8x is 8 times 36 because here angle at center 8x is 2 times this angle. Okay, let me call this angle y. So 8x is 2 times y. Okay, so 8 times 36 is 8 times 6 is 48. 8 times 3, 24, plus 4, 28. Okay, so 288 is equal to 2y. 2y is 288, so y is 144. So 144 degrees is the answer. 144. Can we do this another way? This is first method. Okay, another way we can do it. This first method. Second method would be cyclic quad. This is a cyclic quadrilateral. Okay, x plus y is equal to 180 degrees. Reason: opposite interior angles of a cyclic quadrilateral are supplementary. So we found our x, 36 plus y is 180 degrees. So y is 180 minus 36. Y is 144 degrees. Same way, folks. Same way. Same answer. Different ways, but same answer. Okay? Alright, last but not the least, because of time. Let's do the question 4. And then you watch out for more videos on this. Okay. By the time we solve a lot of problems, you'll be familiar with this. Okay, question 4, last but not the least for tonight. This is JAMB. So at least we've done one from Caribbean, CSEC, then one from JAMB, one from WASSCE, and this last one from JAMB. In the figure below, find PRQ. So we have this. Okay, this one is that other one that I mentioned. So we have something like this. Please do not be tempted to say angles in the same segment. Okay, so we have this like this, and we have O, and they say this is 235 degrees, 235, and then put this here, RQ. Okay, they said in the figure below, find PRQ. So angle PRQ. This is JAMB. P. Okay, P is here. PRQ. So this angle here. All right. So we find this angle here. This is a reflex angle. 235 is reflex. Let's find the obtuse. Okay, angles around the point. So this angle here, angles around the point. If we call this y, 235 plus y is 360 degrees. Angles around a point. So y is 360 minus 235, which is 5, 2, 125. Okay, 125. And then here, let me call this x. Okay, y is equal to 2 times x. Reason, angle at center is 2 times angle at circumference. So 2x is equal to y. So 2x is equal to 125, and x is 125 over 2. Now, JAMB, calculators are not allowed in JAMB. So, Oh, you see, their options has a fraction. Okay, so this will be 124 is 62. 62 is 124. So this is 62.5, 62 and a half degrees. Okay, 62 and a half degrees. Okay, that's option B. Okay, folks, due to time, there are more questions, okay, and you can walk ahead. You can walk ahead of me. I will be posting more as time demands. By the grace of God, I'll be posting more as time demands. By the time you finish all those questions, okay, and like I said, solve it first, then you compare yours with my solution. Okay. By the time you finish it, trust me, you're in the exam hall and you're looking at, hey, where are all those circles? Let me knock it off first. I mean, let me knock it off right away. Okay? Alright. Some of them are tricky. Okay? Some of them in WASSCE theory. Some of them are really tricky, but don't worry. Watch out for more videos. I will explain them. Okay? I will explain them. And even if you don't understand the way I wrote it, I think you will understand it. But if not, watch out for more videos. Okay? Thank you so much for listening. And you have a good night.